sklearncovarianceLedoitWolf. Description: explain in detail. The Ledoit-Wolf shrinkage estimator is a method for estimating the covariance matrix of a dataset, particularly when dealing with small sample sizes or high dimensionality. It aims to address the issue of sample covariance matrices being unstable and potentially misleading, especially when the number of features exceeds the number of samples. Inputs: X. This is the input data, typically a NumPy array or pandas data frame where each row represents a sample and each column represents a feature. Assume centered. This parameter is a boolean indicating whether the data is assumed to be centered. Mean of 0 already. If set to true, the estimator will not center the data internally. Outputs: shrinkcov. The estimated shrunk covariance matrix. It is a square NumPy array where the ij element represents the estimated covariance between the ith and jth features. Shrinkage: the calculated shrinkage coefficient. A value between 0 and 1. A value close to 0 indicates minimal shrinkage, while a value close to 1 implies significant shrinkage. Steps: calculate the sample covariance matrix. The estimator starts by computing the traditional sample covariance matrix from the input data. Determine the shrinkage coefficient. It then calculates the optimal shrinkage coefficient using a formula based on the sample covariance matrix and its eigenvalues. This coefficient controls the amount of shrinkage applied. Shrink the covariance matrix. The estimated covariance matrix is then obtained by applying the shrinkage coefficient to the sample covariance matrix, effectively shrinking the elements towards a scaled version of the identity matrix. This helps to regularize the covariance matrix and reduce its variability. Metrics: Frobenius norm of the difference between the shrunk covariance and the sample covariance. This metric quantifies the amount of shrinkage applied. Average of the absolute values of the difference between the diagonal elements of the shrunk and the sample covariance matrices. This metric measures the impact of shrinkage on the variances of individual features. Visualization plots. Heat map of the shrunk covariance matrix. This visualizes the pairwise relationships between features after shrinkage. Comparison of the sample covariance and shrunk covariance matrices. This allows for a visual assessment of the amount of shrinkage applied. Fine-tune parameters. Assume centered. This parameter allows you to specify whether the data is already centered, potentially improving computational efficiency. Shrinkage. While the estimator calculates the shrinkage coefficient automatically, you can optionally provide a custom shrinkage coefficient if desired. Uncertainty methods. Bootstrap resampling. By repeatedly sampling from the data with replacement, one can estimate the variability of the shrunk covariance matrix. Cross-validation. Splitting the data into folds and evaluating the performance of the estimator on different folds can provide insights into its stability. Challenges and fixes. Challenge 1. High dimensionality with a limited number of samples. This can lead to an unstable sample covariance matrix, potentially resulting in poor estimation. Sample use case that resulted in challenge 1. Imagine analyzing a dataset with thousands of features and only a few hundred samples. Fixes to challenge 1. The Ledoit-Wolf estimator specifically addresses this challenge by shrinking the sample covariance matrix towards a more stable estimate. Challenge 2. Non-stationary data. If the underlying relationships between features change over time, the estimated covariance matrix might not accurately reflect the current data structure. Sample use case that resulted in challenge 2. Consider a financial dataset where the correlations between stock prices can fluctuate significantly over time. Fixes to challenge 2. In such cases, It's crucial to apply the LeDoit-Wolf estimator on recent data windows or incorporate time series techniques to account for non-stationarity.